Greetings, Mendez mathematicians. We're about to start the lesson for the 31st of March. This is Tuesday, lesson 6.6, Building Quadratic Functions to Describe Situations, Part 2. So yesterday you were working with quadratic functions that described a situation where something was falling. Today we're going to look at something where it's both raising and then falling once again, as you had seen last week, the shape of quadratics tends to do. So our learning targets for today are number 1, that you can create quadratic functions and graphs that represent a situation. Number 2, that you can relate the vertex of a graph and the zeros of a function to a situation. And real quick, the vertex of a graph is going to be the center point on the parabola. In this case, up here, this would be a maximum or the highest point of the parabola. And the zeros are going to be when we have x-intercepts. So zeros just mean x-intercepts. All right. So, and the third one is that you know that the domain of a function can depend on the situation it represents. Remember that domain means the input. So if I get rid of some of this, the domain, remember that that means possible inputs. And for today, that's going to be time. So what are the values for time that make sense for the situation that we're representing? All right, let's go ahead and get started. We've got a warm-up where we have a cannon 10 feet off the ground. It launches a cannonball straight up with a velocity of 406 feet per second. Imagine that there's no gravity and that the cannonball continues to travel upward with the same velocity. Complete the table with the heights of the cannonball at different times. We have our input for this table is seconds, and the output is distance above ground in feet. Pay attention to our velocity here. And also that our starting value is that it begins at a height of 10. Question number 2, write an equation to model the distance in feet, d, of the ball t seconds after it was fired from the cannon if there was no gravity. So that means that we're writing an equation to relate t and d, or the distance. Our values in the table, if we substitute in our value for 1, after 1 second we have 10 feet plus the 406 feet per second, so 416. And then as we keep going, we've got an increase of 406 feet per second. Right now we have our equation d equals 10 plus 406t. And if we were to think about what type of function this is, what would it look like if we plotted these points? And I want you to consider for a moment that we have a starting point and we have a velocity, or how much it's growing per second. And that's a constant rate of change. That from 1 second to the next, it's adding by 406. So we have a linear function here, y equals mx plus b, where our 10 is the starting value and the 406 is the slope, or how our change in y, our change in distance, changes every second. So this is a linear function where 10 is the vertical intercept, so b, the output when the input is 0. So that's our y-intercept that we have here. And the slope is 406, which is how many feet it's growing by each second. So that's showing the slope of the line if we were to graph this. So let's take a look now at what would happen if we do actually consider gravity. Considering the fact that we are on Earth, gravity affects all objects that are moving, and so when we're taking into account projectiles or things that are moving, being projected or thrown, the effect of gravity is going to be that this cannonball doesn't just keep going up and up and up forever. It's going to at some point come back down to the ground. So earlier, just now, you completed a table that represents the height of a cannonball in feet as a function of time in seconds if there was no gravity. So this table shows the actual heights of the ball at different times. This isn't quite the same as the table that we had in the warm-up. I'm going to show the warm-up table again. Pay attention to the values for each second. And now for number 1, compare the values in this table with those in the table you completed earlier. Make at least 2 observations. Sample responses. You may have noticed that the actual height values are smaller than the hypothetical ones, except for time equals 0. So at time 0, 0 seconds, both of them have 0, 10. They both start at 10 feet. But for all the other values, the actual heights are smaller than the hypothetical ones from our warm-up. Also, the difference between the distances after the number of seconds isn't constant. For instance, 1 second after firing, the distance is 16 feet. So our hypothetical was 416, and the actual is 400. So that means that the difference is 16 feet. But after 2 seconds, it's actually 64 feet apart, our predicted or our hypothetical, and then the actual value. Our second question is to plot the 2 sets of data you have on the same coordinate plane. So this part you're not necessarily going to be able to enter in your in the Edpuzzle question, but I do suggest that you draw this graph. So take a moment to pause the video and draw this graph. Practice plotting the points from both the warm-up and also question number 1. All right, your graph should look something like this. Our actual heights are lower than the heights from the warm-up that we're ignoring gravity. And how are the graphs alike? How are they different? The triangles in this graph, or the points from the warm-up, form a straight line, and they represent the hypothetical data that ignores gravity. The dots that form a curve, so these dots that are growing more slowly each second, represent the actual heights. Something in common, though, is that they both start at 0, 10. Now we're going to write an equation to model the actual distance d in feet of the ball t seconds after it was fired from the cannon. If you get stuck, consider the differences in distances and the effects of gravity from yesterday's lesson. Okay, so something important to consider when you're writing the equation is that the effect of gravity is to subtract 16t squared feet per second. And that 16 is always going to be the same if we're measuring feet per second, if we're measuring our gravity. So an equation for the actual height of the cannonball is d equals 10, our starting height, plus 406t, coming from our velocity, minus 16t squared, coming from the effect of gravity on the cannonball. We're going to take a look just at how these would look if we were to continue the graphs. The red line here on this graph is d equals 10 plus 406t. So once again, notice that it's linear with a y-intercept of 10 and a slope of 406. So 406 is our rise over the run of 1. And this curve is forming a parabola shape. This is a quadratic function because it has a t squared term. So d equals 10 plus 406t minus 16t squared. We're going to make some observations. First of all, the output for each d value varies across the two tables, across the two functions. When t is 1, the output in feet in the second table is 16 less than the first table. When t is 2, there's a difference of 64 feet. When t is 3, that difference is 104 feet and so on. So the values 16, 64, 144 correspond to an expression that you saw in the previous lesson, 4t squared. The distance fallen in feet as a function of time in seconds. So we can represent the values in the second table with the equation that we had seen down here in number 3. And that's the same equation that we have here that's giving us this blue function, this parabola. So notice that the line that's going straight up, there's more and more distance between the red line and the blue parabola, the actual trajectory or the actual path of the cannonball, because over time gravity is slowing the cannonball more and more. So what do the 10, 406t, and negative 16t squared mean in this situation? The 10 is the vertical position of the cannonball before it was launched, 10 feet above the ground. The 406 tells us the vertical velocity at which it was shot up into the air. The negative 16 accounts for the gravity, the effective gravity on the height of the cannonball after it was shot up into the air. So those are the 3 terms that we have in our equation for this quadratic. The next question, why do you think the graph that represents d equals 10 plus 406t changes from a straight line, so from this red line, to a curve when negative 16t squared is added to the equation? Why does that become a curve? Before that term was added, before the negative 16t squared is added, the height increases by 406 feet every second. Adding negative 16t squared decreases how much the cannonball travels up by some amount, but that amount is getting larger each successive second. So the thing that we're subtracting is larger and larger as t increases. Eventually, the cannonball stops increasing in height and actually starts to fall. Some important pieces of vocabulary that you're going to look at. Can I move this? Okay. Some important pieces of vocabulary that you need to know are vertex of a graph. And see if I can get a pointer to actually work here. Okay, so vertex of a graph of a quadratic function or absolute value function, so something that we saw earlier, previous unit, is the point where the graph changes from increasing to decreasing or vice versa. So it's when we switch from going up to going down or from going down to going up. It's the highest or lowest point on the graph. So here in this absolute value function, it's decreasing, and then we reach the vertex and it switches to increasing. In this parabola, our function is increasing. We're going up from left to right, we reach the vertex, and then it starts going down, it starts decreasing. In our example here, our vertex is this point when our cannonball has stopped increasing. Gravity has slowed it down enough that now it's going to decrease and come back towards the ground. Our next vocabulary word, zero of a function. This is an input that yields an output of 0. So that means in this case, a 0 of the function is going to be an input that gives us a height of 0. This is going to be when our cannonball is on the ground. In other words, if f of a equals 0, then a is a 0 of f. So the main one we would care about in this situation, even though you didn't have to solve for it in this lesson, is 25.4 seconds after the cannonball is launched. It has a height of 0, so that means it reached the ground. So f of 25.4 equals 0, and that's 24.5 seconds, 0 feet above the ground. Okay. Notice that even though this value over here has a positive time value, there is also a negative 0 for this particular function. It doesn't necessarily make sense in this situation to have our domain or our set of inputs be negative because our cannonball was launched at time 0 from a height of 10. So even though our parabola, if we were to graph the function, even though our parabola touches the x-axis at negative 0.025, 0, even though that would be another 0 of the function when we graph it, it doesn't make sense in the story to say that the cannonball touched the ground at negative 0.025 seconds. So in that case, that one doesn't really matter in our real world situation. We come back down to the ground after 25.4 seconds. That's our 0 of the function. All right, and that is your lesson for today. Remember that you can ask your teacher questions and that you are completing the 6.6 cool down by midnight tonight. You are highly, highly encouraged to ask questions before you do the cool down, or to go through this video again if needed before you complete the cool down. Good luck, and hope you are safe and healthy.